Hey, welcome back. In the last two topics, we've been introduced to limits. We know how to find limits graphically, we know how to find them using a table, and we know how to find them algebraically. Today, in topic 3, we're going to be talking about one-sided limits, which means instead of looking at the left behavior and the right behavior and making sure they match up, we're going to be looking at either the left or the right by itself. The way that we write this, if you look right here at this limit notation, that little minus sign right there means from the negative side or from the left. So the way you read this is the limit as x approaches c from the left of f of x. Whereas this positive sign right here means from the positive side or from the right. So the way you would read this would be the limit as x approaches c from the right of f of x. So now we can evaluate limits just from the left or just from the right. So if you've never seen this before, the absolute value of x over x is called the Signum function. It's a good graph to know. Basically, it's undefined at 0 because it's 0 over 0. To the right of 0, it always equals 1. But to the left of 0, it always equals -1. So it's like a flat line that gets broken in half. So example 1 says, find the limit as x approaches 0 from the left of this function. So we're going to write along this function from the left and see what value of y are we getting infinitely close to. Well, from the left, it would be -1. Whereas the limit as x approaches 0 from the right, if I write along this graph from the right-hand side towards 0, I'm getting infinitely close to 1. Example 3, find the limit as x approaches 0. Think back to topic number 1. The limit from the left is -1. The limit from the right is 1. Therefore, this limit does not exist. Next up, when you're evaluating one-sided limits and you're dealing with continuous functions, you're still going to try direct substitution first. Remember, direct substitution means plug it in. So when I look at example 4, the limit as x approaches 5 from the right of 2x plus 4, I know 2x plus 4 is a continuous linear function. So I'm just going to take my 5 and plug it in. 2 times 5 plus 4 is 14. So direct substitution is still plan A for us. It's the first thing we're going to try. For one-sided limits, you just have to know that it's a continuous function. Example 5, find the limit as x approaches the natural log of 4 from the right of e to the 2x. Well, e to the 2x, again, is a continuous function, so I'm going to plug in, giving me e to the 2 times the natural log of 4. Now, using log properties, I can write this as e to the natural log of 4 to the second power, so e to the natural log 16. And because e and natural log are inverse functions, they cancel each other out, giving me 16. Moving along here. Consider the following function g of x. I've got a piecewise function here. Example 6 says find the limit as x approaches 1 from the left of g of x. So I'm going to write along this graph from the left until I get infinitely close to the x value of 1. And what y value am I approaching? 1. Example 7, find the limit as x approaches 1 from the right. So I'm going to write along this graph until I get infinitely close to 1 from the right. What value of y am I approaching? In this case, it's 2. Example 8, find the limit as x approaches 1. Well, we just saw that the limit from the left and the limit from the right didn't match each other, so this limit does not exist. And finally, example 9, what is the value of g of 1? Okay, this is asking not for a limit, but for the actual function value. So I'm looking for a closed dot. It's right there, so the value of g of 1 is 0. Shifting gears a little bit here, we're going to move on and talk about vertical asymptotes. Now, vertical asymptotes occur in a graph when you're at a value of x that would cause you to divide by 0. But remember, if you have 0 over 0, that's actually going to be a whole, not a vertical asymptote. So when we deal with one-sided limits, think about what can happen at a vertical asymptote. A graph can either go up the asymptote to infinity, or it can go down the asymptote to negative infinity. So when we evaluate these one-sided limits, we need to be able to identify where a function has a vertical asymptote. So looking at examples 10, 11, and 12, all we're doing here is identifying where the vertical asymptotes are. So looking at example 10, y equals 8 divided by x squared minus 9. I want to know what values of x make me divide by 0. So I'm going to factor this denominator into x plus 3 times x minus 3. And I can see that values of 3 and negative 3 would cause me to divide by 0. So this has vertical asymptotes at x equals negative 3 and x equals 3. Example 11, x plus 3 divided by 2x squared plus x minus 15. When I see that quadratic in the denominator, I think, can I factor that? Turns out I can. This is going to factor into x plus 3 times 2x minus 5. And when I factor this, what I notice is that I have cancellation here. The x plus 3 on top, the x plus 3 on bottom are going to cancel with each other. What that means graphically is that this function has a hole at negative 3. Okay. What's left over in the denominator? 2x minus 5. That tells me I have a vertical asymptote at x equals 5 halves, because if I plug 5 over 2 into that, I will get a 0. Okay. Example 12. X squared plus 3x plus 2 divided by x squared minus x plus 12. I feel like I should factor everything here in case I have some holes. So factoring the numerator gives me x plus 1 times x plus 2 divided by the denominator. That's going to be x plus 3, x minus 4. So nothing cancels. This graph doesn't have any holes in it. It is going to have 2 vertical asymptotes because of the 2 factors in the denominator. So I can see here I'm going to have vertical asymptotes at x equals negative 3 and x equals 4. Okay, so in order to do one-sided limits at vertical asymptotes, first we need to know how to find vertical asymptotes. So we're going to take these 2 skills and sort of put them together here. So look at example 13. Find the limit as x approaches 3 from the right of 8 over x squared minus 9. Okay. What do we try first? Direct substitution. When I plug in 3, I get 8 divided by 9 minus 9 is 0. So I divided by 0. What does that tell me? This graph has a vertical asymptote at 3. So now I'm going to look at it a little bit differently because I know there's a vertical asymptote there. As this graph approaches from the right, it can only do one of 2 things. Go up to infinity or down to negative infinity. So what I'm going to do is a little trick here. I'm going to pick a value of x that's really, really close to 3 on the right. What about when x is 3.001? When x is 3.001, is this positive or negative? 8 divided by 3.001 minus 9 would be 8 divided by a positive number, which is positive. So this is sort of a shortcut that lets us know that as the graph approaches that vertical asymptote, it's going to become positive, meaning it's going to shoot up to infinity. So this limit is infinity. Now we have to be a little bit picky here. We only say a limit exists if it equals a finite value. Okay? Infinity is not a finite value. So while I do gain some information here, infinity tells me that the graph goes up to infinity and not down to negative infinity. A complete answer would be infinity, therefore the limit does not exist. Okay? But I like to see both of these together because infinity does give you information. Strictly speaking, it's not correct to say the limit equals infinity. The limit doesn't exist, but the graph tends towards infinity there. Okay? Example 14. Okay. Notice this is the exact same question as we had before, so I already know how to factor this. X plus 1 times x plus 2 divided by x plus 3 times x minus 4. So I'm taking the limit as x approaches 4 from the left, and I can see that's going to cause me to divide by 0. I have another vertical asymptote here. So using that trick from before, let's pick a value of x that's really, really close to 4 from the left. How about when x equals 3.999? What happens when I plug in 3.999? I get a positive value times a positive value divided by a positive value times a negative value. A positive divided by a negative is a negative, which tells me that this limit approaches negative infinity. Okay. Again, this is not the complete answer. The limit does not exist because negative infinity is not a finite answer, but this is the complete story. As x approaches 4 from the left, the graph goes down to negative infinity. Okay. Example 15. Find the limit as x approaches 0 from the right of natural log x. Okay. This is one where it really helps to know what the graph looks like. The graph of natural log x crosses through the point 1, 0, grows very slowly as it moves to the right, and sticks to the axis as it moves to the left. So knowing what the graph looks like, knowing that as it gets closer and closer and closer to the x-axis, it shoots down to negative infinity, I know the value of this limit is negative infinity, therefore does not exist. And finally, our last example today, the limit as x approaches 0 of 1 over x squared. Again, this is a good function to know the graph of. I like to call it the volcano function because as it gets close to the y-axis, it shoots up to infinity on both sides. So what we can see here, interestingly, the behavior from the left and the behavior from the right does match up. Okay, from the left it goes to infinity, from the right it goes to infinity. So we're tempted to say the value of the limit is infinity. However, infinity is not a finite value, so the full story is infinity, therefore, does not exist. So to recap, we can find one-sided limits by considering only the left side behavior or the right side behavior of a limit. We can still try direct substitution if a function is continuous, and we know how to find vertical asymptotes by looking for values of x that would cause a function to divide by 0. Combining these ideas, we can take limits at vertical asymptotes and determine if a function goes up towards infinity or down towards negative infinity. Hope that helps. Thanks for watching.